if you think about modern processors, they expose different levels of parallelism, from thread level to instruction level to data level parallelism exposed through single instruction multiple data units. In order to exploit these SIMD units, programmers can continue to code in high-level languages and expect the auto-vectorizers to kick in and vectorize it for you. However, auto-vectorization is not complete. In the sense, it may miss certain vectorizable opportunities. So programmers will go on to hand vectorize codes in certain instances. And in this case, the programmer has used 128-bit SSE2 intrinsics to hand vectorize this code. But however, this creates another problem. Hand vectorized codes are not portable. In the sense, if we ask to compile the same code to a AVX512 machine, the auto-vectorized code can be compiled down without any changes, but the hand vectorized code will still generate SSE2 code because it's fixed to a particular data length. This problem is further aggravated by the fact that Intel has released many vector ISAs ranging from 64 bits to 512 bits. With our compiler technique, however, if we compile this hand vectorized code, we will generate AVX512. So in essence, we can reinstate back performance portability to hand vectorized code using our technique. To illustrate the impact of our technique, let's take a concrete example. In this case, it's a simple mean filter which does an average on a 3x3 window to produce an output pixel value. And we do it for each and every output pixel. And given this simple specification, a naive programmer would come up with the code like this, like what I have shown here. It's completely unoptimized. But the good thing here is compilers can easily analyze this code and it can auto-vectorize it. So if you give a machine which has only SSE2 instructions, it will compute 8 elements at a time instead of 1. And if you expose it to a 512-bit machine, now you can compute 32 elements at a time. But however, if the same specification is given to an experienced programmer, he would generate an optimized piece of code. Among the optimizations that he do are one thing, he can eliminate redundant computation by using rotating buffers. And the thing that we are more interested in is like he will use plenty of vector intrinsics to hand vectorize this code. Then we did a small experiment where we ran the scalar code, that the naive code that I showed you before, vectorized on a SSE2 machine as well as on a AVX512 machine, and then we used this hand vectorized code and we did the same experiment on it. And these are the speedups that we show. Here everything is normalized to the scale auto-vectorized SSE2 version. As you can see, the hand optimized code outperforms the naive version by many folds. But however, it does not scale with the increase in vector data weight. But the unoptimized code scales well because it can be auto-vectorized. So this happens because auto-vectorizers do not handle already vectorized code. They know how to handle scalar code. So if you have a hand vectorized code that's written to a particular machine, and if you want to run it on a newer machine, you will not get benefit out of the newer instructions that are out there. Essentially, it becomes stale. So we introduce a new concept where now we analyze these hand vectorized codes, and then whenever possible, we try to retarget it to use newer vector instruction sets which are higher data weight. And we call this as revectorization. To realize this, we developed a compiler class in LLVM known as Revec. And by doing that, now the hand vectorized code, if we pass it through our vectorization or revectorization pass, instead of degrading performance, it now gains 1.3x performance increase. So essentially, what I have shown here is that Revec reinstates performance portability back into hand vectorized code. And the good thing about Revec is this happens transparently from the from the point of view of a programmer. That means you don't have to change your source code. It happens at LLVM IR level, and it's a regular compiler pass. And we built Revec based on the SLP vectorization technology. The idea behind SLP vectorization is that you can coalesce two or more statements which are isomorphic, that means they are of the same type, and are independent of each other into packs which are later vectorized into vector instructions. We use this concept for revectorization. Here, instead of using vectorizing scalar statements, we can choose isomorphic and independent vectorized statements, which can be revectorized to vector statements of higher data weights. Compared to scalar auto-vectorization, however, we have to deal with further complications because there are vector shuffles as well as opaque intrinsics of which we do not know the semantic meaning of particular instructions. So, to show how Revec works, I'll take a small hand vectorized example here. Revec works on LLVM IR, so we first lower it down into a IR that we are going to consume in the revectorization pass. Next, but in this lowering process, however, LLVM lowers intrinsics in different ways. It can generate generic LLVM vector IR with vector types, or it can generate abstract shuffle vectors for different kinds of shuffles. And sometimes LLVM does not know what a particular instruction does, so it will generate like opaque intrinsic. So in revectorization, we have to handle all of these cases. And now I go through the computation of this particular code. It actually loads. It's very simple, even though there's a lot of words in it. It loads 8 consecutive values from memory, and then it zero extends these 16-bit values into 32 bits, and in the next step it adds 127 to each element in the vector, which are later these 32 bit values are later packed together with saturation into 16-bit values using another instruction, and finally these are stored in a contiguous form in memory. Alright, so in Revec, in order to expose more vectorization opportunities, we first unroll the loop. And this particular code is written for SSC2 machine with 128 bits of vector width. So say that we want to retarget it to a 256-bit machine, which has AVX2 instructions. So Revec first unrolls this computation once. And this results in a computation graph like this, where the same computation is repeated in two times, but it's completely parallelizable. Okay. So if I summarize Revec's transformation, it's similar to what's there in bottom-up SLP work. So we start at a root pack. That this can be like adjacent vector stores or vector reduction routes, and then we revectorize this pack. That means like we retarget it to a higher vector width, and then recursively traverse its operands and try to revectorize those operands as well. And we'll stop whenever we are not able to revectorize a particular pack. Okay, so we'll apply this simple technique to our code example. So here, as we can see, these two stores, we can start revectorization at these two stores because they are adjacent in memory. And instead of two SSC to 128-bit stores, now we can emit a 256-bit store. Next, we go to its operands, and in this case, LLVM represents them as like opaque intrinsics. So we do not know what they are doing. So Revec needs to ask the question, does there exist a matching 256-bit intrinsic that can do the same equivalent computation? To do that, we pre-populate a dictionary of equivalences through enumerative search. This is done offline. And more specifically, we ask the question whether there are k narrow vector width intrinsics whether we can replace a wider vector with intrinsic with k narrow vector with intrinsic. And to establish equivalence, we do random and corner case testing. Corner case testing allows us to remove false positives, and more details can be referred to in the paper. And at compile time, what we do is a simple dictionary lookup to see whether two SSE2 intrinsics can be can be merged into one AVX2 intrinsic. And in this case, we found one, where the same packing operation is available in AVX2 in 256 bits. So we keep on revectorizing. Instead of the two SSE2 instructions, now we emit the AVX2 instruction, and now we want to revectorize its operands. And in this case, both its operands are doing 32-bit addition on using 128 bits. So these are isomorphic, and because of that, we can revectorize them. If we go to the operands of the addition, they are shuffle vectors. So Revec needs to see whether these two shuffle vectors can be revectorized, because they are in an abstract form. So before I go into that, let's see how LLVM represents vector shuffles. It consumes two operands and a mask. The mask decides whether what elements will be selected out of operand 1 and operand 2 to be in the final output. So when you are trying to emit a higher vector with instruction, Revec needs to see whether two shuffle vectors can be merged. In particular, this merging depends on the mask types as well as contents in each of these operands. And we define 4 different shuffle vector patterns that can handle almost all cases in the examples that we have shown. We saw. And I will only go into one vector pattern that applies to the example, to the running example of this talk. So so let's look at the two shuffle vectors that were in the slides. Here, the first operand of the two shuffle vectors are different in the sense we do not know the contents of it. But the second operand are just 128-bit null vectors, and the mask is the same. The deciding factor for the shuffle merge rule to be applied here is the fact that we do not know anything about the first operand in the two shuffle vectors. So we have to do a generic lane widening. In the sense, we have to first see whether 1 and 9 can be revectorized and use that 256-bit value in the new shuffle vector. And for the second operand, we can emit the 256-bit null vector because they are constants. And we recompute the shuffle mask based on proper indexing to make it equivalent to the two shuffle vectors in SSE2 form. All right. Now we have, I have shown how to do shuffle merging. So we use these techniques to revectorize the two shuffle vectors that are consumed by the addition instructions in this example. Next, we go on to the operands of the shuffle vectors I have revectorized, and these are just loads. And fortunately, these loads are contiguous in memory, so we can emit a higher vector with load. And now the revectorization is complete. And when we ask the LLVM backend to generate code, it will generate AVX2 code instead of SSE2, utilizing the full 256 bits of the machine. Next, we did, so how well does this technique work? So we did an extensive evaluation of this technique on certain database operations and on video compression operations and plenty of image processing kernels out there. SIMD-scan is an important database operation used to scan indices in parallel. And it uses variable with integer packing and unpacking as an important operation, sub-operation, and it's done in SIMD. And for this evaluation, we use Lemire's FastP4 SSE implementation that's out there. And we revectorized to a AVX2 machine as well as to AVX512 machine. And the results are like this. We get up to 1.27x speed up on AVX2 machine and on 1.57x speed up on an AVX512 machine. These numbers are for different compression ratios of integers, where a 32-bit integer can be compressed up to down to 1 bit, and it may be not compressed at all, which is at 32 bits. So mind you, we didn't have to do any source transformation. We didn't have to rewrite the code. This is a free speed up given by Revec just by adding it as a compiler pass. And next we extracted kernels from X265, which is which they say is the fastest software-based video encoding for HEVC codec. And we again harvested the SSC2 implementations of some of the kernels out there and ran it, compiled it through Revec. Revec is not a panacea. That means we are not able to revectorize everything. But when we are able to, we get like good performance. In this case, we do not get good. We do not get a performance benefit for the DCT or IDCT kernels, but for dequantization, we get for AVX2 machines, we get up to 1.69x performance increase, and for AVX512, we get almost a 2x performance increase. Next, we wanted to stress test Revec. These are like simple, like a few kernels, but instead of trying it on like tens of kernels, we tried it on like 216 intrinsic kernels that are out there from a SIMD image processing library. And fortunately for us, we had the AVX2 and AVX512 implementations of the same kernels in the library. And these are not only hand vectorized, these are extensively hand tuned and maintained. So I first of all show the speed ups revectorization can get for two kernels. Here, as you can see, Revec gets a speed up, but experts hand vectorizing the code gets a higher speed up. So Revec will, this is because like we are not doing horizontal, we are not revectorizing horizontal operations. This is not always the case. Sometimes hand vectorizing AVX2 kernels to AVX512 gets a slowdown. This is because the developers thought that masked loads are a better way to eliminate the instruction. But in essence, it's actually costly. But when you revectorize, you keep the same original implementation, and you can get better results, even outperforming the hand vectorized AVX512 kernels. So in conclusion, revectorization, I have shown you a technique where you can retarget hand vectorized code, and you don't need to be stale now, and any speed up that we get is completely transparent, in the sense you do not have to change a source code, and Revec helps preserve performance portability of hand vectorization. You can try Revec at this repo, and we'll invite you to try our benchmark suite as well. It's extensive. We have more than 200 kernels there. Thank you.
Thank you. Questions?
The way you presented, at least it looked like a lot of difficulty you have faced was because of the LLVM IR itself. If you had worked at the higher level IR or at the AHT level where LLVM doesn't come out into some of the intrinsics, you probably wouldn't have to face some of the challenges. And second thing is, if you take the code,
Right.
which is written by the expert, and transform it to non-intrinsic code in the first place, and ask the existing vectorization, did you have any experience?
Yes, we did that. So LLVM has a scalarizer pass, which actually scalarizes the vectorized code. But the problem is, if it doesn't know how to do it, like for instance here, there was a packed saturated, where you convert 32 bits to 16 bits with saturation, right? LLVM does not know how to emit scalar code for that. So it will just keep it as vector IR. So you will have partially scalarized code and partially vectorized code. So in auto-vectorizers, we won't kick in.
Time just by fixing that part.
There are tons of intrinsics like that. Like for instance, horizontal addition, like fuse multiply add instructions. which does like vertical addition and vertical multiplication and horizontal addition.
For that you have this offline table of
Yes, yes, exactly, exactly.
Things like circulation semantics are not available in scalars. So there are certain semantics, like otherwise if you want to have say exact overflow semantics, you can't really match those. So when you go to scalars, you lose one of them.
So I had a few questions for you too. Can you explain a little bit why the performance is actually improved when you go say to AVX512? Like what is the core reason? Is it because you reduce instruction count? Is it what? Why is it faster?
So we reduce instruction count as well as we have like larger loads and stores, right? So if we are not memory bound, we are going to like compute on more data at a time, right? So essentially like instead of computing on one like 32 elements, like we can now compute on 64 elements, right? And like that itself it reduces instruction as well as like we are computing at essentially dynamic instruction count reduces.
Okay, which makes a lot of sense to me. Yep. Sorry. Yes. More questions? No. I'll tell you afterwards. Shoot. Yes. I had one more important question related. Yes. Thank you. You mentioned about fuse multipliers and instructions that exist in the bigger instruction set, but not in the smaller one. So you have the ability to recover maybe the application of an FMA when you had a multiply on that in the SSE mode?
No. So that's so here we are not handling non-isomorphic instruction groups. So in order to do that, we can like emit like feed-forward style optimizations. Like say if you find like multiplication by and then addition after that, we may be able to fuse that into a FMA instruction.
If I may, I think that would be a beautiful extension of your work, because this is one of the issues, at least on my side, I have. Oh, there is a new instruction set. There are new intrinsics which are supposed to be faster to do some more complex operations. I would love to that.
And there are thousands of AVX512 instructions which are
I'm
not used at all by
still at AVX2. Yeah.
Have you considered going to a different ISO altogether that is taking Intel code with SSE intrinsics and compiling it for an ARM architecture?
Actually, to do that, we have to do plenty of engineering work, like in the sense like memory models will be different, there will be different exception handling. So I think it has to be done at the dynamic level. I mean, it may be doable. It may be doable, but it will require a lot of engineering work to figure out the differences between two ISAs. I mean, it's not just simply extending data width or like replacing an intrinsic with another intrinsic. We have to deal with other global context as well.
I think probably on that direction an easier but still interesting question will be going from AVX512 to SSE. Have you considered that?
Yeah, we haven't, but that's essentially scalarizing. It's similar to scalarizing, right? You are instead of going down to complete scalar, you go go down to like from 512 bits to 64 bits or 128 bits.
Yes.
So I mean, it can be done, but our pass does not handle it.
Can you say a bit about the equivalence checking that you mentioned, K1 equivalence checking?
Right.
Because I mean, some of the low-level details like AVX512 instructions may require memory to be aligned with 64 byte boundary, right?
Right. So it's not formally verified. So what we did was like we had like around 6,000 corner cases, which checked for like certain alignment problems, and then there are instructions which have greater than, equal to, and greater than semantics. So they will only differ in one or two cases, right? So if we did random testing, we won't catch that. There will be lots of false ones. So we like catered. We have around 6,000 corner case testing cases to like eliminate those false ones. But it's not formally verified.
And haven't you considered that this is a step which is obviously useful, but you can see that it's a matter of time before it gets annoying to have, let's say, always older code, which was written for obviously obfuscate processor that will be by a number of gradual transformations into something modern, wouldn't it be value and say, okay, listen, shouldn't we do it at the source level, if only because it will allow the source level to be maintained with current scales, and probably also simplify the source.
Right, but the problem with source level is you program using intrinsics, right? So at that point, like these are like just text. You don't you don't know the semantics. Like say for instance, what does underscore add means? Like is it an addition operation? It can be something else, right? It's just text. So, but at the LLVM IR level, we know what kind of instruction it is, right? Is that what you want?
Okay, think of I
Yeah,
cannot
yeah.
disagree with the statement, but
Right.
what I'm trying to get at is that if you're about to rejuvenate the source code has to some degree more value.
So you want like a source-to-source compiler instead of like it may be doable, but then you need like a intrinsic map, like the map that we built, the dictionary, like for all instructions, instead of like the instructions that LLVM does not know.
Or maybe the tool is a way to convince the person who are maintaining the code, hey, there is performance on the table, now maybe you want to go back and do the source code change.
Yeah, it's a matter of time before the person who wrote it is dead, and that.
Actually, that's true. That's true. In Photoshop, there's like certain kernels like nobody wants to touch because that person has left. And, and even if you touch it, like the performance becomes downgraded. Like it degrades performance instead of increasing performance.
Because if you do produce little bit different output, that's really more. And a lot of times people do optimization that become basically features of the corner.
Okay, maybe one more question.
So you said a couple of times that we don't know what semantics is of these text things in source, of the intrinsics, LLVM-IR, and you have like this database where you map them and have testing and all of that. So first of all, I disagree with we don't know the semantics. We know the semantics of all of those.
No.
It is defined.
No.
Somebody defined that, otherwise you wouldn't be able to implement it in the first place.
Actually, like there's a paper on this, like we stratified synthesis in PLD 2006.
They have problems in their definition, but somebody defined it because otherwise the compiler wouldn't be able to do something with that.
I disagree with that. Like for instance, like even Intel does not know. I mean, like whether the implementation is correct. Like
I don't say about correctness.
Yeah.
I don't argue about correctness,
right.
But the compiler does something with that string, right?
But
You know what it does. The compiler knows what it does. You kind of look at it and you take the result of what the compiler did, but you argue you don't know what the string means. The compiler knew what it meant.
compiler doesn't know what it means. Like for instance, if it's like say packad, well, it will generate like intrinsic it doesn't know about, and then the backend what it does is like there is a one-to-one mapping from that to a x86 instruction.
Yes.
That's it.
Okay, let me table that for a second.
Yeah.
So then we have tools that actually allow you to come up with small patterns, like pattern recognitions by formal verification that say the following set of instructions is equal to the following set of instructions.
Right.
So basically, you could now come up with your translation table for also the scalar case. So you can come up with scalar code that has the same semantic or proof that it doesn't exist as your intrinsics do. We have tools for that. You have to define the semantics of the intrinsics.
Exactly, that's the problem.
The semantics has to be defined because your processor is executing
I mean,
something.
I would ask you to read the stratified synthesis paper by Alex Icon and group. Like they say like these semantics are not available. Like where does this semantics exist? They try to automatically synthesize the semantics as Boolean circuits, right? So and they have done a good job up until like AVX2. But if you want to go to AVX 512, like you need to reapply it and see whether it generalizes at that. That paper is like it will clarify your plot. Like these are not documented.
I don't have a problem with
Okay, so I think you guys have a good discussion for lunch. It's time now. Let's thank the speaker for the. Thank you very much.